Hello and welcome back to Calculus 2. The last section of chapter 9, we're talking about calculus of power series. And in this whole lecture ends with one sentence. Do it term-wise. Done. So you have some function, you transform that function with the power series into polynomial, and what is the way you integrate and differentiate polynomials? Term by term. So one sentence ends the entire lecture, and then we just need to do some examples and see what are the subtleties of this, because you can't just expand anywhere you want. You have to be very careful because of the situation of convergence. Remember, more terms, better convergence for longer interval, and so on. So what I have here is we say that the function f of x will be equal to the sum 0 to infinity of ck x to the k, right? And then if I am integrating f of x dx, I will actually be integrating the sum of ck x to the k dx. And we know that we are dealing with a polynomial. So essentially what I'm doing is I am integrating or differentiating, whatever it is, c0 plus c1x plus c2x squared plus c3x cubed plus dot 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 times dx at the end. So we have to be very careful on where to center our calculations. And we have seen those graphs. If you don't remember, go back and watch the video for 9.1, where I used Mathematica to show the difference in convergence and how far the convergence goes if you have one term, two terms, three and four and five terms for sine function. So every time when I added an extra term, there was a wider interval at which you can use the polynomial to compute values. So now, if you are aiming to integrate e to the x squared dx from, this is problem 30, well, it's not problem 30, they have negative x squared. Whatever, I'll just use positive x squared. Let's say from 0 to 0.25. Well, you look at the limits over here, and expanding anywhere in that region is going to be okay. And then you can use, maybe three terms should be fine to deal with this. So we integrate. So I'm going to expand from 0 because 0.25 is very close to 0, so it's okay to expand at 0. You can, if you're paranoid, go expand at 0.1, right? Or in the middle at 0.125. You can expand at any value between 0 and 125. You can also 0.25, you can expand there as well. It's just for convenience, we want to expand at 0, and we know that 0.25 is not that far away, so it's okay to expand at 0. So I have 0, and then I'll put this as a 1/4 on top. And we know that we get 1 plus, and now this is going to be x squared plus x to the 4 over 2, and we can get x to the 6 over 6, it's fine. One more term, and I am throwing the rest away. Now, this is not equal. This is going to be approximately equal, so we put the squiggly equal sign in between the two. And now you see that you are dealing with integration of basic polynomials, right, which you should be able to do in your sleep. So it's x plus x cubed over 3 plus x to the 5 over 10. And finally, x to the 7 over 42, computed from 0 to 1/4. And now you plug in 1/4 everywhere. 0 will kill all the terms, so we don't care about 0 in this case. So this is 1/4 plus 1/3 times 1/4 to the 3rd power, plus 1/10 times 1/4 to the 5th, plus 1/42 times 1/4 to the 7th. And then that's going to be equal to some number, okay? And that is done. So something that cannot be integrated at all was converted by the power series into a polynomial that we can just do whatever we want, right? Well, polynomials are nasty to find roots, right? So it's not free lunch throughout, but they're very easy to integrate and differentiate and, you know, do a lot of other stuff like compute values. So polynomials are in generally good, and they're just very evil when you have to find roots. To find roots for a quadratic, you have to use quadratic formula. To find roots for cubic, well, those formulas are insane, right? The fourth has, you know, few pages procedure, right? And then there is a proof that shows that polynomials of degree 5 and above do not have formulas or methods to find roots. So you have to do numerics every time, right? So polynomials can be nasty in that respect, but for differentiation, integration, limits, and calculating values, they're probably one of the easiest, right, in the neighborhood. Like e to the x rivals because e to the x itself on the integral and derivative. Obviously, that's easier than polynomial, but then computing values with e to the x is a living nightmare. So that's why polynomials win, right? When you look at the overall. So you just go and figure things out. You have the expansion, you replace the function. If it's a composite function, you replace the function what it needs to be, and then you're done. Problem 39 looks cool. I don't have to solve any of these anymore. It's just we can discuss. Problem 39 goes from negative 0.35 to 0.35 of the cosine of 2x squared dx. Now, some of you study mathematics to learn, and some of you study mathematics to pass, right? Those of you who study mathematics to learn, you remember the theorem from Calc 1, which says that if you have even function on a symmetric interval, you can make 2 times 0.35, and you have cosine 2x squared dx. This is something that you cannot integrate because you have cosine of x squared. None of the methods you learned would work here because you need that x in front for basic u sub, or you need something else to do integration by parts and stuff. So simply nothing will work. But you can expand this, and as you can see, what I did is I moved that negative 0.35 to 0. I don't have to do that. I can just expand this at 0, and it would be even on both sides. But it doesn't matter. It's an even function. So if you know the formula, you do it. Why not? So now what do we have? In this expansion, I have 2 times the integral 0 to 0.35, and now I need expansion. Cosine starts at 1. The next term is negative, and it's all evens. So it should be x squared over 2 factorial. So x squared, it's going to be 2x squared over 2. Plus, the next term is 2x squared to the 4th over 4 factorial. And we can add another one. 2x squared to the 6th over 6 factorial. And then dx. Again, I don't know why I need to put the squiggly equal sign, because this approximates the value up there. So now what do I have? I have 2 times the integral 0 to 0.35. And over here I have 1 minus, this is 4, this is 2x to the 4th, plus, this is to the 4th, it's 16 over 24. 16 over 24, cancelled by 4. No, cancelled by 8. You get 2/3, right? So 2/3 x to the 8. And finally, 6 factorial is 720. And we have 2 times 2 to the 6th. That's 64. And then you have x to the 12, and you reduce that, and it's dx, right? So when you equal to some number. So we started from something that we cannot integrate at all, which is cosine of x squared, and then we turned it into this power series, which is just a polynomial, and you just now play with these coefficients, all right, and you're done. You plug in 0, and which kills everything. It's polynomial, and 0.35, and double it at the end. Derivatives do the same. Derivatives do the same thing. So you go term by term, and you compute these. So that's it. Oh, actually, for differential equations, you will need to know how to take the derivative of a power series. So let's just write that real quick. So in differential equations, you are going to assume that the solution is y equals summation of Cn x to the n starting from 0 to infinity. Now you will need the first and the second derivative to plug into the second order differential equation. So to find the derivative of this, so your y prime is going to be summation, and it will start at 1, go to infinity, and now you have your coefficients, which is Cn, that copies over. Now the derivative of x to the n. What's the derivative of x to the n? N x to the n minus 1, yes. It's a polynomial, right? So it's just n minus 1. So now all of this is a constant, and you have the variable part over there. Now, neither of these can escape the summation because summation operates on n's, so everything has to stay inside. Now, if you take a look at the counter shifted, exponent shifted, so these two guys are no longer compatible to be added. So that's where I said you have to do some peeling and mathematical gymnastics to get them to look the same, so you can combine them under the same. Which are those rules 1 and 2 that we covered on the properties. The second derivative of a power series will push the counter even further to 2. You will have your Cn and then n, and now when you differentiate the x to the n minus 1, it becomes n minus 1 x to the n minus 2. So as you are differentiating power series, you're just differentiating polynomial. You know that to differentiate polynomial, you drop the power as is down, and you subtract 1. Now you just have to bring all the extra baggage, and you need to know that the counter shifts by 1. Honors section of the course are supposed to supply the proof of why is that counter shifting by 1. And if you actually do the proof, you will see where it comes from. As you do the limit definition of derivative on the power series. You know the limit of f of x plus h minus f of x over, yeah, that one. So you use that one on this, and you will see that the counter shifts by 1. So you are not going to use this in this class, but you are going to use this in your differential equations chapter 3. So, the sooner you see this, the better. And it's also, it's a part of the lectures here. It's just we don't use it for anything right now. And it is great to end our exploration of power series with the only thing that I really understood well and was very happy with when I saw it as a student when I did this sequencing series and power series. and that is to see sine and cosine power series written next to each other, like one above the other. And here's why. So sine x, right? I didn't understand it. I still loved it. I didn't understand it. So it took me some time to get used to this, about 3 months. But then when I got it, it was a joke. So when you write your sine, you get your x minus x cubed over 3, not 3, 6. Well, 3 factorial. Plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial plus x to the 9 over 9 factorial minus 3 dots forever. Right underneath that is a cosine x, which is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial plus x to the 8 over 8 factorial minus dot 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 forever. Why would something like this make me happy? What do you think? Well, we established that it's a pattern, and if you add them together, you get everything, right? You'll see 1 and the x squared, x cubed, x4, x5, x6. Yeah, so that's great. Yeah, the pattern is there. But there is something else going on that, and I waited to this to the end to put it in the calculus section of power series. So clearly something that I'm looking for would be a calculus concept applied to this. Beautiful. Derivative of sine is cosine. Go on. Take it term by term. What's the derivative of x?
1.
What's the derivative of x cubed? 3x squared. You see that 3 knocks off the 3 factorial into 2 factorial? And you go term by term. So next time someone in Calc 1 tells you, you say, oh, derivative of sine is cosine. Why? Let me develop the entire chapters 8 and 9 for you so that I can answer why. You start that on a napkin, all right? And you get it, right? And there you go. And if you take the derivative of cosine, it's going to become negative sine. You see the derivative of 1 is 0, but then the derivative of x squared over 2 is 2x over 2 canceled, becomes a negative x. See that? So it's a negative x. So the derivative of cosine is negative sine. So that was the first and maybe the only thing that clicked for me when I was a student doing these things, because I did it wrong. I tried to use the common sense and things like that. No, just learn the sheet I gave you, you'll be fine. Right? You shovel some algebra around it, and you're good to go.
Yeah, I thought he said shit. He said sheet, bro.
Yeah, sheet is the paper with all of these. Yeah.
He moved back there at the beginning of the class. He's like, I'm doing the project with my guy, and then he said that. He told us. So he announced it.
I guess we are done with this one.